أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. In today's lecture we will be discussing about Gibbs Paradox. This lecture is taken from the course outlines of the statistical mechanics having the course code of PHY231. We have some objectives from today's lectures. The first objective is to understand the Gibbs Paradox. We also need to know the entropy, the basic concept of entropy. So let's come toward the brief survey of thermodynamics. We have basically 4 laws in thermodynamics. The 0th law is not mentioned in this slide, but anyhow, first of all we will discuss the 3 laws and then we will come back toward the 0th law of thermodynamics. The first law of thermodynamics gives us the concept of energy, and that basically describes that energy is always conserved. It means that we cannot create energy nor we can destroy energy. Of course, we can convert the energy from one form into other form. Say for example, we can convert energy from one form, just like we can convert potential energy into kinetic energy and kinetic energy into potential energy, similarly chemical energy into mechanical energy. So different form of energy we can convert from one form into other form, but we cannot destroy the energy by itself. So this is actually the first law of thermodynamics. And basically, in detail, if we look toward the first law of thermodynamics, it is mentioned that the energy that is given to any particular system, that is partially used in increasing the internal energy of the systems, and partially it is used in doing work. So again we have some restriction on various configuration or application of the first law of thermodynamics, but this is the simple statement of the first law of thermodynamics. Now we are coming toward the second law of thermodynamics, that is regarding the entropy of the universe, and it states basically that the entropy of the universe always increases. We have 2 different statements regarding the second law of thermodynamics. The first statement, one statement is that we cannot convert 100% energy into work. And the second statement is that we cannot extract heat from cold body toward hard body without the expense or expenditure of energy. So normally in daily routine we observe that heat can move or heat can be transferred from hot body toward cold body when both are brought in thermal contact with each other. But if we want to move the heat or we want to transfer the heat in the reverse direction, by reverse direction I mean from cold body towards hot body. So what we need to do, is it possible spontaneously? No, the answer is no, it's not possible spontaneously. We need to waste some energy to move or to transfer the heat from cold body towards hot body. So this is the other statement of the second law of thermodynamics. But the basic understanding of the second law of thermodynamics is that entropy of the universe always increases, and it means that when we are considering an engine, so part of that energy will be utilized into work, or that will be converted into work, and part of that will be wasted. So we don't have is not possible to have an engine that is 100% efficient. So this is the second law of thermodynamics. So in other words, it's also cases normally says that entropy of the universe always increases. So now we are coming toward the third law of thermodynamics, and that says that entropy of a perfect crystalline substance is taken as zero at the absolute temperature of 0 K. This is the third law of thermodynamics that says that entropy of a perfect crystalline substance is taken as zero at the absolute temperature of 0 K. So these are actually the three laws of thermodynamics. If we come toward the second law of the zeroth law of thermodynamics, then it states that it basically gives us the concept of temperature and thermal equilibrium. That is, if there are three bodies and two of them are in thermal contact with the third bodies independently, then the two will be in thermal equilibrium with each other, and that basically gives us the concept of temperature, because we measure the temperature by this phenomena or by the zeroth law of thermodynamics. So this is a brief history of the laws of thermodynamics. So now we are coming to understand the concept of entropy a bit more, and we are considering different systems for this purpose. And this is the simple example where we have two gas molecules that are non-identical gases. I mean, the molecules or the nature of the molecules is different from each other. So this is called to be non-identical gases. If we look toward this slide, here on this side we have yellow balls, and on this side we have red balls. So what will happen if we mix the gases with each other is the entropy of this system will be increases or it will reduces. So let's come toward the next slide. This is the next configuration when the two gases are mixed with each other. It shows obvious increase in entropy or disorder, because the two gases that were of different nature and it were separated initially, when these gases are mixed with each other, then the entropy of this system increases. So this is the final configuration of this particular system. So now we are coming toward the other example. This example is a bit different because the gases what we are going to mix with each other is of the same nature, or in other words, we can say that the molecules are identical to each other. So this is actually called as the mixing of identical gases. So what will happen to the entropy of these systems when we are mixing the identical gases. So the nature of the molecules is same. These molecules are of red color, and similarly these molecules are also of red colors. So what will happen when we mix this molecule with each other? Look toward this slide. The gas molecules are allowed to mix, and what happened? This is the final configuration after mixings. It actually shows zero increase in entropy, as the action is reversible because the gas molecules are of same nature. The molecules are identical to each other. In this simple example, you see that the color of the molecules is same. Even we cannot identify the molecule from each other. We cannot distinguish the molecule from each other. It seems to be same. So what was actually the Gibbs opinion regarding the previous examples? And the Gibbs, basically the opinion regarding this was that when two non-identical gases mix and entropy increases, so we imply that the gases can be separated and return to their original state. And the second case, what was the second case? When two identical gases mix, then what happened? It is actually impossible to separate the two gases into their original state, as there is no recognizable difference between the gases. This was actually the Gibbs opinion regarding the mixing of non-identical gases and identical gases with each other. So actually these two cases stand on different footings and should not be compared with each other, because the mixing of gases of different kinds that resulted in the entropy change was independent of the nature of the gases. So this is something we need to note, that the mixing of gases of different kinds that resulted in the entropy change was independent of the nature of the gases. So therefore, so that is why it's independent of the degree of similarity between them. So we have this simple understanding. On vertical side we have entropy. Here at this point, when we are looking toward this curve, the value of entropy is 0 at this point. S is equal to 0, and at this point the value of entropy is maximum. So that is why S is maximum at this point. Similarly, at this point the value of z is equal to 0, and at this point the value of z is equal to 1. So what was the Jain's explanation regarding the paradox, regarding the example, regarding the entropy, what we discussed before? See, if we consider a macro state, we already know the difference between the microstate and the macro state, and we already understood in the previous lectures that there are different microstates that are possible in a given macrostate. So as in this particular case, S is actually the entropy, that is equal to K log W into C. Here S into X is the entropy that is associated with a chosen set of macroscopic quantity, and the other factor, that is actually W into C, is the phase volume that is occupied by all the microstates in a chosen reference class C. So this thermodynamic entropy, that is actually S into X, is not a property of a microstate but of a certain reference class Cx of microstates. So that is why generally that for entropy to always increase, what we need to do, we need to specify the variables we want to control and those we want to change. So what happen? Any manipulation of variables outside this chosen set may cause us to see a violation of the second law of thermodynamics. So this is basic results, that any manipulation of variables that are actually outside this chosen set, it may cause us to see a violation of the second law of thermodynamics. So we have one resolution regarding that, and there are some new factors that are introduced in the equation regarding the entropy, and that actually use the quantum mechanical approach to discuss this problem. So the equation that was derived is very clear and is written here. According to this equation, S is equal to minus into nk divided by 2 into 1 plus alpha log into 1 plus alpha plus 1 minus alpha into log into 1 minus alpha minus 2 log 2. And in this particular case, alpha measure the degree of orthogonality which is the degree of similarity between the gases. So when alpha is equal to 0, then the entropy of the value of the entropy is at its highest peak, or it is at its peak, that is carry its highest value. And when alpha is equal to 1, then entropy is its lowest value, and that carry the low value in that particular case. So therefore entropy decreases continuously with increasing similarity. So this is some opinion about this resolution. So the curve is drawn here again between the entropy. The entropy is on the vertical sides here. Look toward this arrow bar, and the similarity is on the horizontal line. We have two values for entropy. The one value is when entropy is equal to 0, and the other value is when entropy is equal to maximum, that is X maximum. And this is actually the value of similarity. Here we have the value of Z, that is equal to 0, and here we have the value of Z, that is equal to 1. So resolving the Gibbs paradox using entropy and its reverse relation with similarity proposed by Lenshaw, and it shows basically a connection between information theory and entropy. It proposed that entropy increases continuously with similarity of the gases. It basically gives us the concept that entropy increases continuously with similarity of the gases. So a question arises that why entropy increases with similarity. So basically due to Lin proposition that entropy is the degree of symmetry and information is the degree of non-symmetry. So basically we have three concepts. The first one is that high symmetry, and there will be high similarity. The second is the entropy, that is actually the information loss, and similarity is also the information loss. So entropy is equal to the information loss. So basically an increase in entropy means an increase in disorder of that particular systems. An increase in entropy means an increase in disorder of that particular system. So a decrease in entropy reflects an increase in order. So if we look toward this sentence, that a decrease in entropy reflects an increase in order. So a more ordered system is more highly organized. So thus possesses greater information contents. So let's come toward the other example. And in this example we have this similarity, that is actually the information loss. We have one particle on the left side. This is the one particle here, look toward it, and this is n minus 1 particles. You see, we have n minus 1 particles here. So for a system with distinguishable particles, information on n particles is equal to different information of each particle, and that is equal to n pieces of information. So for a system with indistinguishable particle, if we have particles that are indistinguishable particles, so information of n particles, that is equal to information of one particle, or that is equal to one piece of information. So this simple example elaborate the similarity, the information loss, or the different information of each particle for n particle, for one particle, or for n minus 1 particles. So we can conclude from this that high similarity, that is normally a high symmetry, there is greater information loss. So again we can come towards the concepts of high symmetry, that is high similarity, the entropy, that is actually the information loss, and similarity, that is actually the information loss. So from this we can establish the link between the various concepts. If we consider a system to be highly symmetrical, so it should have high similarity, and we will have greater information loss for this purpose. And then when there is greater information loss, there will be higher entropy of that particular systems, and they will be symmetrical, and that will come directly from this case. So this is the type of steps that need to be taken to move from high symmetrical systems towards high entropy of that particular systems. So where there is a way in resolving the paradox, we need to discuss the different opinion of the scientists, and then we can compare that. So this is something about the Gibbs paradox and its understanding. Thank you very much.